I would like to thank Juan Antonio, Maria, and all the organizers of this event. And congratulations again for this great program. And without further ado, let's start the session. I will introduce our first speaker, who is Stefano De Luca, and he's a policy analyst in the Digital Policies Unit of the European Parliament, where he performs research on telecoms, IoT, liability of emerging technologies, and digital economy. The title of the talk would be Submarine Communication Cables, Security and Resilience in the EU. So the floor is yours.
So good morning all, and thanks a lot for hosting us today. We will host you back tomorrow, and it's very nice, this cooperation, and it's not the first year. So I will address indeed submarine cables, starting from the definition. Submarine cables are fiber optical cables that are laid down on the ocean floor. It's very strategic for the EU for different reasons. Actually, 99% of international internet traffic pass through them. And it's very important for the EU 3 member state islands, for example, Cyprus, Ireland, and Malta, for the other islands that we have in general in Europe, and also to connect us to the outermost account region. Now, why it is a challenge? There are two primary challenges here. The first one is physical attacks to our submarine cable infrastructure. And the second one is the cybersecurity attack to such infrastructure. When we speak about physical attack, we are speaking about the cutting of submarine cables. They can receive actually severe damage. Imagine that around the world, we have 1.5 million kilometers of submarine cables, more or less 900,000 miles. And it's almost impossible to patrol all of them. In terms of cybersecurity attacks, well, here we have different forms of attacks. It can be tapping into the submarine cables. It can be access to data. And if you read the NISA report on submarine cables, so our EU cybersecurity agency, they states that generally they are quite concerned more on attacks on the landing station, the landing points, so in the port or beaches where actually the submarine cable networks will connect to the underground internet infrastructure of the member states. Why? Because in this landing point, it's maybe easier to develop DDoS attack, malware, and so on, also on the software running the system. Whereas tapping directly in the cable, when it's under the sea, it's a little bit more difficult, according to ENISA. Even though there are think tanks reporting a different point of view, and also military are concerned, for example, that during repairment of such submarine cable, or when landing such submarine cables, foreign actors or malicious external actors can actually put some backdoors inside. And also on the fact that with evolving submarine technologies, it's also possible maybe in the future to tap directly in the submarine cables, even under the sea. Well, another thing to say is that the submarine cable network has a high level of redundancy. This is true for the most part of Europe. So by cutting just one submarine cable, you won't shut down the internet traffic in the EU. What is redundancy? Redundancy is actually rerouting the traffic when you have a problem of congestion or a severe damage and so on. In other routes, it can be other submarine cables, but it can be also other different means. However, we should keep in mind that in case of multiple coordinated attacks on submarine cables, and as I said before, for that kind of EU member states island or little islands across Europe that are really relying on them, well, the problem might be different. On top, there is always also the citizen perspective of security. So how they will, the sense of security that European citizens have after an attack, and also little disruption that should be taken into account. Another thing is, as a challenge, are repair vessels. In Europe, according to a report, we are just 3 repair vessels, 2 inside the European Union and 1 in the UK. So you can imagine that in case of a coordinated attacks over our submarine cables, having just 2 ships or 3 with cooperation with the UK to take care of them, well, it might be an issue. Now, what is the state of play here? Security of submarine cables is not something new. Actually, it started back in the time, so we can just study history, and you will see that in the Spanish-American War, so end of 19th century, the US Navy cut the telegraph submarine cable system of Spain, connecting with the Philippines and Cuba. So it was really a cut of the telegraph communication system. And this is also true for World War I and II. Indeed, the hostility between the UK and Germany started with the Royal Navy cutting the telegraph submarine cables between Germany and the Americas. Well, why it is now, since 2022, that policymakers are putting so much stress, focus, and enforce on the security of submarine cables, where actually, after the invasion from Russia to Ukraine, we saw an increase of incidents in submarine cables, in particular in the Baltic Sea. We saw indeed that since 2023, there have been already 10 attacks and incidents on submarine cables, and according to the majority of analysts, this might be linked to action of third countries, so hostile action of sabotage, so-called even hybrid war. Well, now we need to think about what the EU is doing, right? We have a legal framework. There was the European Electronic Communication Code, where Article 40, Article 41 was taking care of security of electronic communication network. How? By actually requesting to put in place some organizational and technical measure to protect the electronic communication network, but also through some reporting obligation of incidents and vulnerabilities of the network to the competent authorities. And in case of where appropriate, so in case, for example, of a cross-border incident affecting more than 2 member states, to notify the other member states and our cybersecurity agency, ENISA. Well, now the ECC, Article 40 and 41, just Article 40 and 41, has been replaced by the NIS2 directive that protects the essential and critical infrastructure of the European Union. The NIS2 is a kind, is it called, of all hazard approach. It means that it defends both against physical attacks and against cyber threats. What is important to state here is that submarine cables have not been really listed in the essential and important operators entity of the NIS2, but we can find in the recital that submarine cables are actually covered and that they must be subject to the same reporting obligation of telecoms network, for example, so without undue delay or maximum 24 hours when there is a security incident, reporting that to the competent authorities. Then in 72 hours to try to add a little bit of details on the type of incident and so on. And in 1 month by 1 month from the incident to write a proper report on that. It's also true that the NIS2 directive reports that submarine cables should be included in the national security strategy of the member states. So also organizational technical measure, how to protect it, what member states are planning in order to protect such infrastructure. What are the problem of these two directives, though, the ECC and the NIS2? The late transposition. What happened in the European Electronic Communication Code is that the due date for transposition was end of 2020, but the last member state actually transposed it in November 2024. The NIS2 directive, let's see, but we need to see if it will be transposed on time, because it should have been transposed by October 2024. But on 7 May 2025, the European Commission had to send a letter, so a reasoned opinion against 19 member states that had failed to notify the full transposition of the NIS2 directive. The last two legal framework that we need to take into consideration is the recommendation on secure and submarine cables of February 2024 and the communication that is the EU Action Plan on submarine cable just 1 year later, February 2025. Why? Because the recommendation and the communication are giving us some guidance on how Europe is planning to address the security and resilience problem of submarine cables. For example, the action plan states that all operators of submarine cables should be covered under the NIS2, so it urged member states to transpose the NIS2 by including all operators of submarine cables. It created an expert group formed by experts from member states and ENISA in order to do a new wide assessment and mapping of vulnerabilities of the submarine cable networks in the EU. It wants to build a cable security toolbox, likewise the one on 5G, so to try to detect which are the high-risk vendors and try to avoid them from our submarine network. Stress test, but in particular to build an EU cable reserve fleet for this kind of repair vessel shortage that we have. I don't know, maybe you might follow the US example that is putting $10 million per year to actually fund 2 different repair vessels that have a special contract with the US government. So also in case of war, where the other companies that have a commercial agreement can stop for force majeure, these 2 vessels need to go and operate also operate in the sea. And this is very important, actually. Just a few things. The flag of the ship, it's American. The sailor should be American. So there are some criteria to respect. I finish just with some think tank recommendation to use the EU Defended Fund in order to fund sensor and security system or drones helping for the surveillance of the submarine cable networks in the EU, putting in the license requirement for laying cable to use this sensor as a clause, and then pushing EU government to rework a little bit the UN Convention on the International Sea. Why? Because it creates quite problem now if you're not in the coastal and territorial water to do our research and on board on a ship that might do, let's say, like the Russian Shadow Fleet, some kind of strange movement in the high sea. And that's all. Thank you.
Okay, let's have the questions for the end of the session as before. So now let me introduce our next speaker, who is Diane Leblanc-Albarel, and she's a researcher at the COSIC group at KU Leuven, and her research focuses mainly on perceptual hash functions, which are used to identify similar but not identical media, time memory trade-off attacks, and authentication and password manager protocols. So she will be discussing on ChatControl EU regulation, impact, and risk. So.
So thank you very much for giving me the opportunity to speak here today. So as you say, I'm a postdoctoral researcher at Leuven, and I'm working on applied cryptography and also on perceptual hash functions that are used in real-world systems, like the ChatControl regulation that is the subject of this talk. So in 2021, in response to growing concern about the spread of child sexual abuse materials that I will call CSAM in this presentation, the European Commission proposed a regulation that is commonly known as ChatControl to stop the spread of this CSAM in the Europe. So the idea was to make mandatory for platforms to scan user communication to detect and report illegal content such as CSAM. So normally, our private message in the EU are protected by a directive that is called the e-privacy directive, which prohibits this scanning. But in August 2021, a temporary exception was introduced, allowing companies to voluntarily detect CSAM while awaiting a permanent regulation. So thus, since 2021, several major companies such as Meta, Google, Snapchat, TikTok, Microsoft have already been scanning for CSAM in Europe. And this platform detects CSAM. When they detect CSAM, they automatically report them to the US National Center for Missing and Exploited Children, that is called NCMEC. And this organization, NCMEC, then forward them to law enforcement agencies, including European authorities. So now I will talk a little bit more about how we detect this CSAM. So there is basically two types of CSAM. The non-CSAM, meaning the CSAM that have already been detected. And these CSAM are the vast majority of CSAM online. And so they are detected using what we call perceptual hash function. And so there is also a second type of CSAM that is new CSAM that we never detect before, and those ones are detected by AI. In this presentation, I will only talk about the first type, so the non-CSAM, because the ChatControl regulation is about non-CSAM only, and that really are the vast majority of CSAM that are shared online today. So first I have to explain a little bit what is a perceptual hash function. So here basically you can say that a hash is a kind of fingerprint of a media, and most of the time it's an image. So here, for instance, you have a free picture and the corresponding perceptual hash, or you can think of it as a fingerprint. And the particularity of perceptual hash function is that for same image or close image, the hash will be the same or very close. So here, for instance, you have the same dog in two different poses, then the hash is the same for these two dogs, but for a cat that is totally different, the hash is also totally different. That's the idea. So this hash or fingerprints are very useful because they allow us to store information about this picture without storing them. Because as it's CSAM picture, we really don't want to store this kind of image because they are horrific, and because if there is a leak, then you leak image of child sexual abuse. So yeah. And so instead, organizations like NCMEC, which is a bigger organization that fight for stopping the spread of CSAM online, in fact have database containing tens of millions of non-CSAM hashes like that. And every time we detect a new CSAM, a new hash is added to this database. So how do we detect them then? So we have, as I say, database with tens of millions of hashes of CSAM. And so when you upload a picture on Instagram, for instance, the platform computes the hash, the fingerprint of your picture, and then check if this fingerprint is in the CSAM database. If it's not in the CSAM database, no problem, nothing happened. But if it is in the CSAM database, then report is the user is immediately reported to NECVEC with all the information about his account and the picture that have been flagged as CSAM. So in theory, it's really working well. It's really precise, but the problem is that in practice, it's not exactly like this. So, yeah. So until first, I have to say that until really recently, so just a few years ago, these perceptual hash functions were only analyzed by the company that built them, and security researchers only began analyzing them in the very last few years. And we have found some our findings are concerning. So first, what I can say is that all publicly analyzed perceptual hash functions have been broken in a matter of weeks or months, and that false positives are really, really common. So what I call false positive in when two different pictures share the same hash or very close hash. So for instance, this is a collision false positive we have found. So these 2% share the exact same hash, but they are not the same person. And so false positive at scale, what does that mean? That means that if a picture of you, for instance, have the same hash than a CSAM picture, then you will be reported, even if the picture you just upload is not at all CSAM. So that's the problem of false positive. And during my own research, we have analyzed the Apple function and Microsoft Meta function that is the most used for CSAM detection. And we have found that first, the false negative rate is very high, between 20 and 50%. False negative means it's when you should have the same hash, but you don't. So that means that you then miss, for instance, a CSAM. We also have a very high false positive rate. So this I already explained for these two. What is also possible is to create collision. So for instance, you have two pictures. So one is CSAM, one is not CSAM, and their hash. And what is possible is to implicitly modify one picture so that its hash corresponds to any other hash. So for instance, you take a CSAM picture, you modify it imperceptibly, so the picture remains the same, and then it's not hash of a CSAM anymore. So this is also possible. And so this is the research on perceptual hash function, but real-world data confirm this. For instance, the Irish authorities published that in 2020, only 20% of received CSAM reports were actually CSAM, and more than 11% were clearly non-CSAM. So it was family picture on beach or other thing like that. And there is one other thing about this regulation that raise concern for us is that it will be mandatory for any services, any communication services, included encrypted one, so included, for instance, WhatsApp or Signal. And then if the communication is encrypted, then the only way to detect or to scan the image is to scan them directly on the user phones, for instance, or computer, which is also, how to say it, concern for privacy of citizens. So that's for the technical part. And so how is it going, this regulation? So in the European Parliament, a majority of deputies opposed to this regulation, mostly due to concern about threat to privacy and encryption. In the Council of EU, it's a little bit different. Currently, there is a majority of states that are in favor, but they don't represent 65% that is required for the adoption. They represent around 63% of EU population. So there is a blocking minority led by Germany that continue to oppose it. And so in February 2025, Poland proposed a compromise to make the detection voluntary again, but that under 16 years, people would be banned from platforms that could host CSAM. And to ensure this, platform will need to verify user age with notably official ID, for instance. So this proposition, instead of resolving the debates, have created new division and new disagreements have emerged around it. So now it's even more stuck. So that's how it is in the European Parliament and Commission. And if I can give my opinion and the opinion of my colleague on this as a cryptography and privacy researcher, we have mainly three concerns. First, the technology simply doesn't work. Second, it's extremely intrusive. And third, it's easily abusable. So when I say technology didn't work, so it produced really a lot of false positive, and also it's not really efficient as the rates of false negative is also really high. It's really intrusive because mandatory detection will mean scanning private communication and in some case scanning personal device, and it will be an unprecedented attack on privacy in Europe. And on top of that, the ID check for online access that is proposed since February 2025 can also destroy online anonymity. And third, it's also easily abusable. So it's really easy for criminals to manipulate picture, to hide illegal material or launch false accusation. And yeah, so, and also once such a scanning system exists, there is no guarantee they will be used only for system detections. They could be reused for other kind of surveillance. So in that time, we agree we have to fight absolutely against systems because child sexual abuse are very serious crime, but to do so, we should focus, we think, on solutions that are effective, respect fundamental rights, and are scientifically backed up. So, for instance, a good starting point, but it has already been said, will be transparency, because today the perceptual hash function used in detection are often secret. So it's companies that have built them that keep them secret. And we should also demand that their design may be public or at least open for independent review so that they can be properly evaluated and improved. And at the end, my final word would be, I think that more than a technical question, this kind of regulation, I think, confront us with some essential question, like where do we draw the line between protection and freedom, and how far are we willing to go in the name of safety?
Thank you very much, Diane. So let's move quickly to our next speaker, who is Romain Jacob. He's a researcher at ETHZ Zurich, where he leads the Sustainable Networking Research area of the group. He performs research on communication protocols, real-time scheduling theory, and statistics applied to experimental design, among other topics. So give you the floor.
All right. Good morning, everyone. So far this morning, we talked a little bit, or we heard a little bit about digital technology, AI, and others as part of the solution. My work is more to try to quantify the impact of this technology as the problem. Thankfully, nowadays, there are a growing body of research studies that look at the digital impact, the environmental impact of digital technology. Those are really hard to get right, but let's assume they are. Let's assume those studies are well made. The focus of my talk today is to raise the awareness on a second problem, which is that the outcome of those studies can be very easily misinterpreted. I want to give some example of those potential issues and how they apply to my own research field, which is the internet. And by that, as a scope, I will mostly focus on the wired part of the internet, not the wireless, which is slightly different, slightly different challenges. So what should you be aware of when you look at the sustainability of ICT? I want to highlight three important methodological choices that you can make. There are more of them, but those three, I think, are some of the predominant one. The first is the differentiation between what we call the operational versus the embodied footprint. I think my colleague Jukka will talk about this more later in the session, but briefly, operational cost is the cost that you have when you run something, and the embodied is all the rest of the costs. So the cost for manufacturing, the cost for deploying something, the cost for recycling it. And the important takeaway here is that the digital infrastructure may, in some cases, be cheap to operate, but we should not forget the embodied costs for manufacturing and deploying, which highly dominates consumer devices and dominates also in the internet infrastructure. The second important dimension to be aware of are two different types of reasoning on the data, which we call attributional versus consequential reasoning. Attributional reasoning is essentially the way you do accounting. You take an entire system, say, I don't know, OpenAI as a company, and you can look at the entire footprint of that company, and you can look at the amount of service they provide. And you can, for example, use such reasoning to assess the footprint of a ChatGPT query, for example. Consequential reasoning is different. It is about what is the impact of a specific action you're taking or decision you're making, right? It is to say, if I now connect my laptop to the internet, I connect to ChatGPT, and I run one more query, what is the footprint of that extra query, right? And so we have both ways of looking at what is the footprint of a query, but two different ways of looking at the problem that will lead to highly different numbers. I'll give example of that, how that applies to the internet in the second part of my talk. Finally, the third dimension I want to highlight the attention to is relates to time aspects. Right? It is extremely important to differentiate what we call direct effects versus systemic effects. Right? So the intuition is I think is pretty clear. The direct effect is the cost of doing something now, right? Like if I run a ChatGPT query on my laptop now, what is the cost of this right now? Whereas the systemic effect are more long-term societal and durable change in how we do things, right? A prominent example of that is for transport. There's an argument that if I don't take that plane today, the plane will still fly, and so the impact of me not taking the plane is marginal, is almost zero. The systemic effect is that if nobody is taking the plane anymore, then the plane will not fly. And the COVID pandemic was a primary example of this, where all of a sudden all the planes were grounded, not because they were not allowed, but because there was nobody to put them in the plane. Right, so just to recap briefly, things to pay attention to: are we talking operational or embodied? Are we talking attributional or consequential? And are we talking direct or systemic effects? Let me now give you two examples of how those, let's say, not paying attention to those dimensions may lead to very important misunderstanding. The first example I want to give you is from Netflix. Netflix has been one of the first large digital organizations to make a serious effort at estimating their environmental footprint. In the latest report I looked at was from 2022. Their ESG report was reporting an average number of 55 grams of CO2 equivalent per hour of streaming. Right. This intuition, when you see this number, is that if instead of streaming Netflix tonight for an hour, you go on a walk in the park, then you would save 55 grams of CO2 emission. This intuition is completely wrong. Right? So if you read that number and you think about this in this way in your mind, you're completely off guard of it. Here's why. Well, because this number comes out of an attributional analysis, right? It's an accounting exercise where you take the entire footprint of Netflix and then you divide it up by the total number of streaming hours for an entire year. The issue is that when you look at how this number comes from, what is in the total, the actual delivery of the streaming content of Netflix represents only 3% of the entire footprint. And the footprint is dominated by the production of the movies and the series you stream. Right? So whether you watch it or not, the movie has still been produced and that footprint doesn't go away. Right? So the number is not wrong, just like you interpret it wrong. It has implications for policymaking because when you're seeing such number and then you say, well, then maybe if we reduce the video quality of the next streams, then that may have positive downstream impact. Well, it may, but not on that number. That number is not going to be affected by this because the delivery of the content is very little to do with Netflix footprint. But as I say, it may have other benefits, which leads me to my second example, which is the power cost or the energy cost of sending information over the internet. The order of magnitude to keep in mind is the following. To send traffic over the internet, it roughly costs nowadays 1 watt for 100 gigabit per second of traffic. For those of you that don't work in networking every day, 100 gigabit is maybe a bit abstract. Where I live in Switzerland, the standard fiber connection to the home is 1 gigabit per second, right? So if you think about 100 houses that are all simultaneously fully utilizing their fiber connection, whether they do this or none of them do this is 1 watt power difference, right? So it's very, very small. And so, as I was saying before, once you know those numbers, right? If you say, if I stream in 4K, if I stream in lower resolution, the power difference is going to be almost negligible. I mean, it will be negligible. But that is only the direct effect. And this is where there's been some disagreement in the community between, like, should we do this or should we not do this? If you look at it from the direct effect perspective, whether you send traffic or don't send traffic, the power difference is small. However, if you send more traffic, you increase the demand. And that creates a systemic effect, which is essentially the rule of supply and demand. As more and more users send more traffic, request more traffic from the internet, the demand rises and the network operators respond. They respond how? They respond by deploying more capacity, deploying more submarine cables, building more data centers, deploying X and Y. And those deployments have very significant costs. Operational, because operating them requires energy, and embodied, because we need to manufacture and deploy all those things. So it is complete when we assess the implication of such a study, we need to think what we are considering. Are we targeting the reduction of operational versus embodied, but also direct effect versus long-term effects? So to conclude and wrap up, I think my main takeaway for today is that those studies are being produced. Those are hard to make, but even if we make them right, they are easy to be misunderstood. And it's hard to explain those things briefly to a non-technical audience, which is what I try to be doing today. So to recap, 3 important dimensions. There are more, but I think those 3 are really the key. Operational versus embodied. Takeaway is the embodied part is very significant in the digital infrastructure. So if you omit this, you're very likely going to draw wrong conclusions, or at least biased ones. Attributial versus consequential. When it comes to policymaking, we usually want to enforce something. So we are talking about a change in behavior. If you want to inform this decision, what you need is consequential reasoning. So stop taking the accounting numbers for doing this because you're going to get wrong. And third is direct versus systemic. And in the case of the internet, what we observe is that the direct cost of something may be very small, but still have very large systemic effects downstreams that we see happening. It's not an hypothesis. So to summarize, sometimes people kind of this analogy that the internet is a set of, roads on which, packets traverse, like information traverses those roads. It works, to the extent that the analogy works to the extent that sometimes the pipes are full and sometimes they are empty, right? But if you have a road, once the road is built, you don't spend energy whether there are cars on the road or not. The internet is not like that. It's actually kind of the opposite of that. The internet is more like an hyperloop tube, like those big vacuum tubes, and you spend a lot of energy to make the vacuum in the tube, whether you have trains going at full speed in the tube or not. Right? This is what's happening in the internet today, and that's something that needs to be fixed. Thank you.
Thank you very much, Romain. Our next speaker is Patrice Nivaggioli, who is an AI solutions engineer at Cisco Systems, where he drives innovation in AI engineering and operational practices. He supports the EMEA region, ensuring customer business success through cutting-edge innovation and strategic guidance. And he's also responsible for 2 courses on software and security at École Polytechnique and Telecom Paris. So today he'll be speaking about quite a critical subject, which is data center energy footprint and LLM power inference. So, the floor is yours.
Thank you. Thank you, everyone. Thanks for having me. Thanks, Juan Antonio and Maria, for the organization. And thanks for all the very smart talks. And it's a very good pleasure for me to be there today. So I'm going to talk about very concrete things we see in the field building data centers. So I'm part of the team involved on building data center in the US and also in Europe. So data center for me is something around a few hundred of GPUs to 10,000 GPUs. So it's the scale factor is a little bit different depending on the companies, if it is hyperscaler or enterprise, corporate. So the thing I would like to discuss with you, only 5 things. Those 5 things are around not to do too much with computer science for 3 of them. It's more about the cooling, the power, the silicon, right? Those things are really changing in the real world today. So we need to work around some of the constraints to make sure that we can scale the data center, right? To handle AI application, right? So the main driver today for data center is not too much the cloud application or the web application as we used to know, but we do see a very huge impact of AI. This is a few data here, right? So showing that the amount of energy required by data center in the US is around 4% of the production of energy in the US for the data center today. But the prediction is more around 12–15%, right, in the coming years. So the way the increase in terms of need for power for those data center is really huge. And it is the only industry or the most impactful industry in terms of power consumption. So the acceleration is very fast. What we see also in the data center, right, is that the repartition of the energy is around the servers and the cooling system, how to compute things and how to cool down the computation, right? This is the main factors. What is hidden in that numbers is that part of the servers now you have the communication. As you may know, the GPUs, they are talking to each other, right? It's an AI system from an infrastructure point of view, is really a collective communication system. It's very different from what we see on the internet with TCP/IP and so on. So part of the server now, you have a lot of acceleration, not only for the computation of the tensor and so on, but also for the communication between the GPUs. So the first thing is the cooling. Very practical things. What we see in data center today is this kind of things on the right-hand side for me, where you put systems in the rack to cool down the air, right? But you still have an air exchange between the compute and the communication system and the air, right? Then the thing is here you don't have too much density. What we want in the data center is to put, unfortunately, a lot of servers, right? And to have a very high density of that. In that case, just sweeping that. I have the screen. I cannot see the screen here, right? So, sorry. So the density is not very good. In this kind of rack, you can put 3 or 4 servers, right, with GPUs. And what you want to achieve is much more. Why? Because having a low density data center means that you need to build data centers, right? And what I'm not explaining here is the cost to build data center, the concrete and the things like that. It's very expensive and very impactful, right, from a resource point of view. So to cope with that, we have system now where we put the fluid, the cooling fluid directly to the systems, to some systems. So the CPUs or the GPUs or the DPUs, the things moving packets very fast. It's what we call direct to chip, right? Today we are building system with that. If you look at the big data center at OpenAI or even in Mistral, right, they are building things with this kind of technology. It means that you can achieve 150 kilowatts per rack. But the way you operate things now is a little bit different. You need plumbers, right, in your data center because it's a very complicated thing to bring a cooling liquid to hundreds or thousands of GPUs, right? So the plumbings around the data center is very, very difficult. Imagine in your house plumbing could be difficult for few tubes, right? Here it's a very difficult operational things. And then just here, right, you have the immersion cooling, what we call immersion cooling. You can achieve much more density, right? It's the new system we are seeing with that. The constraint with that is you need new servers, right? In the servers, you don't need the fans, right? Because if you put fans in this kind of tank, right, you will have a kind of mayonnaise at the end. So nothing is moving in the fluid. You have things like you don't need to have, or you don't want to have stickers also on the motherboard. If you look at the compute, you have stickers everywhere, right? So we are rethinking the way we are building servers to put them in this kind of dielectric fluid. From an operational point of view, you have things that are not vertical anymore, but horizontal, right? So it means that the maintenance is a little bit different. When you take a server out of the fluid, right, you need to dry the server before to be able to operate on the server. So, but anyway, this is the kind of technology we do see, right? We have a project in France with a big bank. So even enterprise, not only hyperscaler, are going in that direction. And here, from a policy point of view or environmental point of view, you can imagine what kind of fluid you have here, right? Is it organic? Is it good for the health of the guys maintaining the things and so on? So there are a lot of things about standardization, regulation that are still to be discussed, right? Because today it's mainly proprietary system. The next thing is the silicon. So we discussed a little bit about the performance improvement on the internet. We are working a lot as a company in Cisco to optimize the power of the equipment. So you have the silicon. The only way to do things at very high speed is to have your own silicon, right? So developing silicon today, the state of the art is 4 nanometers, right, for the switch and the routers. And here you can see the change, right, from the past generation, right, where it takes around 4 watts for 100 gig interface without the optics, with the new generation where we are at 2 watts, right? So the idea is to move forward in that direction, but we are already at 4 nanometers, right, silicon. So the next step is to go, and maybe for academic, it's interesting, is to go photonic, right? So some people at the Cornell University, they are building a photonic switch, right? To move forward and to avoid to go from optic to electronic, right? Because here you have dissipation and it's not really efficient. The other thing that the industry is doing is working a lot on the pluggables, on the opticals, because those guys are consuming a lot. And here you can see the difference efficiency you have been having something you build at 100 gig per second, right? With switching at 100 gig per second, or you aggregate things at 800 gig per second. It's much better to have big interface that you can break out. And today, this is the way we are building data centers, right? So we have very big switch. 800 gig is the standard, right, in large data center. We are moving to 1.6 terabit per second, right? And then you are using breakout because you have a very good optimization. Here, by 2, I'm optimizing my switching at 100 gig. I have 2 watts here compared to 5 watts if I'm only using 100 gig interface. 2 minutes. The other thing that is also evolving is the way you give energy to the data center. Try to avoid the conversion between AC and DC everywhere. So to bring directly DC power to the data center, because what we are doing on the switch or the servers, we are converting from AC to DC. So better to convert at the origin, right, at the entry point in the data center. The other thing is now more on the software side, and I have just 1 minute to finish on that. The thing is, AI, from an infrastructure point of view, is a collective communication between 100 or 1,000 of devices, right? You need to optimize that. Today, it's not optimized by far, right? So here, there is a report from Saclay, which is a cloud provider in France. Small installation, few thousand GPUs. It's not very big, right? But the efficiency of those collaborative communication is only 50%. So when you have a GPU, right, H100 GPU at $200K, right, it's only used as 50%, right? Because all the other time it's idle because we are waiting for another GPU to compute the tensor and so on. So there is a lot of work to be done here, right, to improve the intercommunication between the GPUs. And the last thing is on the model itself, right? So we talk about the large model. The bigger is not always the better, right? So what we do see now in the industry and what the vendors are doing is to provide specialized models that are very efficient and low footprint, right? So in that case, we have just released as an open weight model, the foundation SEC. It's a 8 billion parameters model. And here you can see the evaluation on a very specialized topic, which is cybersecurity, where we have much better accuracy compared to a larger model, which is in that case, a 70 billion model from Llama. So in that direction also, using very specialized model, it's critical. The problem with that is not to train the model. It's I would say it's an easy thing, is to get the data set. And it's a nightmare to get very accurate data set to train and to make your model very efficient. Sorry if I was a little bit too long. Thank you.
So last but never least, we have Jukka Manner, who is a full professor of networking technology at Aalto University in Finland. His research and teaching focuses on networking, software, and distributed system, with a strong focus on wireless and mobile networks, transport protocols, energy efficient ICT, and cybersecurity. So today, Jukka will be explaining and discussing about life cycle emissions of ICT infrastructures.
Okay, thank you. So I have a great spot before lunch, so I'll try to keep this entertaining but also educational. So I'll be maybe summarizing a bit what Romain said earlier, and maybe highlighting in the first session there was a lot of AI, so showing how, or maybe discussing how AI is one of the biggest environmental catastrophes humankind has ever invented. So if that doesn't raise the interest, then I don't know what can. So as mentioned, so I've been a professor at Aalto University for about 20 years now, and let's say these data centers that was in the previous talk have been the biggest news in the Finnish media in the past week, actually even almost past half a year, given about a dozen interviews in the past week to TV, radio, media on the problem that there's so many data centers coming to Finland that we don't have the electricity to power them. And of course, in Finland, there's a lot of wind power coming, but what if it's not windy? You don't shut down data centers, you don't shut down AI, you don't shut down your digital services if it's not windy. So there's a bit of a problem coming, and not even a small one. And the scale is that, the Finnish electric energy grid will see 10-20% increase in the next few years. 10-20%, so where does that come from? But electricity is just a minor detail in all this, all these problems. So I have 3 slides, but lot of things. That one. Okay, so there's a lot of small details. The point is not for you to read them, but you can ask the slides later. Maybe I'll start with an analogy. The left upper picture is from Volvo. So they did a life cycle analysis of petrol cars versus electric cars. Now, of course, everybody thinks that driving an electric car is good for the environment, but take into account the manufacturing costs. Manufacturing batteries is an environmental catastrophe. And that, for example, picture talks about the life cycle emissions when you drive the car for 200,000 kilometers. Only after that you start seeing the petrol car being a black version. And the graphs are about the source of the electric energy, whether it's the global average, EU average, or Nordic, which is pretty green. But then at the same time, you need to understand the upper right-hand picture is from United Nations Economic Commission for Europe, analyzing the electrical energy emissions from different energy sources. And by far the greenest energy source is nuclear. Nuclear, the one that we don't build anymore here. So there's a bit of a problem, in my opinion. And wind doesn't, comes close, but not even, in the same Same scale, hydro, yes, and of course, let's not talk about burning coal and stuff, but nuclear is the way to go, and that's continuous energy. With wind, you know, if it's not windy, then what do? We burn something. So that, of course, that doesn't work. The lower left-hand side corner is just an illustration that what the future will hopefully look like eventually. That's the average emissions from the electricity generation in Finland in the past dozen years. Look at the graph and the shape of the graph. You can look at the numbers later if you want, but it has dropped by 90%. We are getting close to, you know, Sweden and Norway, not yet there, but close. You know, 10 times less emissions than EU average, for example. I think France is also very close. So, okay, the emissions from electrical energy generation are coming down, which is, at least in some countries, are coming down, not everywhere. Then on the lower right-hand corner is the LBL analysis of, for example, data center energy use in US and the expected increase. You can see that it's almost an exponential curve. So the absolute number of energy needed for data centers is just, you know, crazy. And if Finland is going to 20% of national energy consumption, that's a, you know, major concern, in my opinion, and everybody agrees that if it's not windy, then what do we do? Nothing. But anyway, that's a small problem. Let's take the left-hand corner is emissions from manufacturing a smartphone. That's with different, that's for an Apple iPhones and different sizes of memory. So it matters how much storage space your iPhone has or phone has. And, you know, if you take an average, you know, 100 kilograms of CO2 equivalent for manufacturing one smartphone. If I use the smartphone in Finland, the electricity I need to charge my phone in Finland will reach 100 kilograms in over 200 years. So taking the other way around, the life cycle impact is manufacturing, it's not the energy consumption. And if you take the upper right-hand corner is just an analysis of this e-waste, which is coming to market, and what is the recycling rate of the e-waste. It's just, you know, microscopic. You can get these slides, you can look at the details later. So of course you can ask me the slides from the organizers. Lower left-hand corner, again, too small to see, but the colors are important. The recycling rate of smartphone components. Point is how much red is there, which is recycling 0%. If you think about your smartphone, it's not recyclable. Hey, please don't, you know, lie to people. I mean, there's, okay, the shell can be recycled and the glass, and that's about it. I mean, if someone thinks that, you know, taking your smartphone to the store and it's recycled and you get the green feeling, then don't get the green feeling. So the recycling isn't, but that's your smartphones. You take the same phenomenon for servers, your AI GPU things, the amount of materials mining that is needed to build those is just insane. Of course, they don't affect, you know, Europe, unfortunately. You know, we pay for the electrical energy, but the emissions for manufacturing those is even worse than the increase in energy consumption. And the lifetime of your GPUs are, I don't know, 2 years, 3 years, and then out, and next one's in. Recycling 0. So what is, of course, needed is, you know, the repairability. Of course, the French repairability index is a great thing, and in I mean, EU has the same coming, this, you know, repairability understanding, and I think that's something that should be much more developed in the future. I mean, but it applies not only to ICT, your washing machines, your TVs, anything, as you know, repairing your washing machine, you know, costs more than buying a new one. So why would do that? I mean, that's what it is currently. My phone's screen is broken. 500 euros to replace it. I'm waiting for a few more scratches and then I'll replace it. So, you know, I drop it from time to time. So, but I mean, 500 euros to replace the screen. I mean, geez, I mean, that's, okay, it's repairable, sure. but it's insanely pricey. So who would do that anyway? You know, again, so the repairability is there, but maybe the economics isn't there. So again, there's maybe some work to do, at least on the EU level, to make that decent, especially if we think about the citizen. But, you know, same as, you know, servers, you know, network equipment, anything, you know, the repairability isn't there. So last slide, hopefully I'm not going overboard. Left side is actually done by an analysis done by my colleague at Aalto University. So what are the emissions from Aalto University's use of ICT? And the upper left-hand corner says, I need to check, 81% of our emissions from using ICT are manufacturing the devices we use. Laptop servers, screens, projectors, you know, meeting room panels, stuff like that. 81% is manufacturing, not the energy use, not our cloud services, not our data center energy use, manufacturing. And if you look at, you know, the lower part is, you know, breaking down the manufacturing different, you know, categories, but you can get these slides, so you can look at that, you know, later. But it's mostly the laptops and screens and so forth, which are, you know, the biggest concern. And I think that was even calculated by Margareta Björksten, taking very, let's say, optimistic lifetimes of laptops and servers. With lower lifetimes, this, you know, 81% is even higher than that, if the lifetime of the laptop is not, you know, high enough. So to conclude, I mean, we really need to kind of understand also the manufacturing side, the whole kind of life cycle of ICT, thinking about, you know, on one hand, reducing the usage, because manufacturing every single device is a huge, you know, environmental burden. Thinking about reusing them in some other purpose, not just decommissioning immediately. So maybe the old GPUs could still be used by someone else, potentially, and also understanding that the recycling, I don't know if you could say it's a scam. It's not a scam because, you know, people are doing it, but it's not really working. And for example, as an example, I was taking part in a seminar, was it 2 weeks ago, at Aalto University of electric cars. And there was a great presentation on the recycling of the car batteries. And even today, the recycling rate, which is economically feasible, is this much. And with the new chemistries coming, the batteries, it's this much. So there's nothing, no incentive economically to recycle car batteries at all. No one will do that voluntarily, unless, you know, regulation or someone starts paying you to do the recycling. So just as a point that, you know, it's not just the ICT sector, but many other sectors have the same problem, that we don't necessarily need to, you know, understand the big picture, including manufacturing and recycling, which isn't really there and stuff like that. But hey, hopefully I didn't go overboard. I didn't at least get the warning, so I'll stop here. It is.
Yeah, thank you. Thank you very much for all these presentations. I think it's become quite clear that a lot of challenges that we are facing with our modern infrastructure for communications and computing. I think it was quite a realistic panorama. And yes, let's move to questions.
Thank you for the presentation. I would like to, okay, you mentioned that 80% is the manufacturing impact, and 80%, and the usage is low. But how important is the manufacturing impact actually? It was not clear to me. I mean, compared to other manufacturing activities, etc. Because for example, if we use renewable energy to manufacture the for the machines that manufacture, or I don't know, recycling material, etc. I mean, okay, I understand the difference between manufacturing and usage, but how important is, how heavy is this manufacturing actually?
Yeah, so as mentioned, you know, if you look at the whole emissions that using ICT at Aalto University, what is our environmental footprint? Then it really comes from actually all the devices we buy, which are built so that we can use them. Same, take an analogy of cars, an electric car. It's not green if it's just sitting in your, parking place. And it only becomes green over time when you use it more, and it's, greener than these petrol cars. But there is a huge amount of embodied, like Romain said, embodied, people use that embodied, emissions in the manufacturing.
Okay,
So,
but your percentage was about specifically the ICT devices, compute, etc.
Yeah.
So is the manufacturing of these devices heavy, I mean, for the environment or not?
Yeah, it's an environmental catastrophe. It's not heavy, it's a
How
catastrophe.
can we measure this?
I mean,
compared to other
and that's Margaret. I can put you in contact with Margaret. She has tried to find all these, emission calculations. I mean, I used some of my lectures and talks from, for example, from Dell. You can find an interesting reports on the emissions from manufacturing one Dell server. How much emissions from manufacturing that server are emitted? So all the chassis, all the mining, everything included in manufacturing that.
So if comparably, if 80% of emissions for manufacturing is very high, then the 10% also is quite high, I mean, compared to other activities. So
yeah, I didn't compare that to all the, warming the buildings in winter at Aalto University and all the lights and everything. But the point is that we often neglect to understand that these devices don't come from thin air. And say, especially with AI, which is needing huge, I mean, there's a crazy boom in increasing these, data centers, more electrical energy consumption. But again, the electrical energy comes from somewhere. The consumption comes from somewhere, which means that there are new servers, new GPUs being built. And that's not visible in Europe because nothing is built here in terms of ICT.
Some academic works speak about flexibility of data centers to adapt to production, etc. Do you think this is feasible or not? Because I have heard that the operators of data centers are not at all favorable of this kind of flexibility.
No. When you power on your data center is full load and that's it. I mean, if you want to run your AI, you don't. The problem I see, especially related to Finland, is that when the data center presses the on button, it starts using 100 megawatts, 200 megawatts. I mean, Microsoft is deploying 3 data centers worth 600 and something megawatts in the capital area. Someone needs to provide that energy somehow. If it doesn't come from wind, then we need to borrow it from, Sweden. Hopefully.
Okay. Sorry, but it's not the objective too, but the question is very interesting. But why a country like Finland, somehow they attract this investment in data centers? Why on the other side, you don't, motivate the investment on, I don't know, hydro or other, or the energy sources? I mean, given the problem of energy feed of the data centers, why you develop a policy to attract more and more data centers if you cannot support them?
Well, that's what I've been telling to the Finnish media, and it doesn't make sense. I mean, no one looks at the big picture, and then and data centers are not flexible, as you know. I mean, when you put it on, it's on, and that's it. And no one looks at the big picture. People say that it's gonna be okay, but no one has shown the numbers that it's gonna be okay. It's not gonna be okay with that model. I mean, someone suggested that for the data centers to bring in flexibility, they have these diesel generators as backup power. So when it's not windy, they fire up the diesel generators. Okay, so that's the green solution, right? So you have gigawatts of diesel generators burning diesel because it's not windy someday in Finland. So that's a crazy idea. And as you know, storing electricity isn't here today. It might be in 20 years, but it's not in this decade anyway. So it is a major catastrophe coming. Yep.
It's very currently,
Yeah.
Reinforce interconnection in Norway or.
Yeah. As I said, Sweden hopefully will save us. Any Swedes around? Please help us.
Okay, thank you. Mengdu again from the Netherlands. First, thank you all the speakers. Thanks for the courage to tell the truth. You also let me feel that I'm not the only one in the minority. I told the same story very often. People dare not to, they don't want to listen to that. And also just a quick answer to the previous gentleman's question. So there's a top research institute in Europe. It has been already several years ago, probably published, compare with the powertrain about the electric vehicle with the current combustion engine. Nobody dare to talk about combustion engine anymore. So the powertrain, look at the supply chain, the life cycle, is 3 times more unsustainable compared with the current system. And now you have 2 systems. That's a factor of 4. So we know basic math. We know how these things were, the independent researchers have done. So a lot of things were hidden. I'm really happy to listen to all the speakers, all your insight. The question is simple. Is your speech supported by any publications? Can I get your relevant materials, publications?
Yeah, of course, from my talk, just drop me an email, there's plenty of paper. But if you look at my slides, I try to use not my opinion, but public data, which shows that we are going, in the wrong direction. If you it's about putting pieces together, looking at that number, and putting that together, you realize that the end result is not good. So you don't necessarily need academic research to look at these public sources, which hopefully are trustworthy sources, and then looking at the math that this doesn't look good, especially the Finnish situation currently. No one has done that, and I've been talking about it and getting a lot of angry company people after me because I say out loud where this is leading. Of course, politicians want investments in Finland, but that's their role. But then if you look at the national level, and I wouldn't even dare to calculate how much emissions are created somewhere on this planet because of these data centers needing these GPUs and servers and all that equipment. So, but that's another story. But it's kind of always, maybe this is not a political statement, but if you think about Norway as the greenest country, 80 whatever % cars are electric, or 90% whatever. But where are they manufactured? Not in Norway. So someone has created insane amounts of emissions so that in Norway the road traffic is green, then somewhere else it's really black. Of course, everybody knows where that is, but
Yeah.
Someone else give pointers. Romain, you have a lot of pointers to give on the.
One of the reason the embodied footprint is less known is because also it's much harder to do, because a lot of things when you start thinking about the manufacturing cost of something, you have an entire supply chain and you need to define boundaries of how far down the chain you go. And there's a lot of argument being made in the research communities of what should be counted in and what should not, what makes sense to count and what should not. That depends on the type of reasoning you want to make, the type of study you want to, or the type of behavior change you're trying to impulse. It's not trivial at all. And this is why it's also a bit difficult. It's easy to measure the operational because you put a power meter, you get a number out, you can convert this to carbon emitted for the electricity production. We don't do this nearly enough. We should do it more. We should have more transparency, but that's easier, definitely easier. And I think Jukka's work and a lot of other people's work has been trying to put the emphasis that should not be the entire picture, because it isn't. And the manufacturing is a big problem. And so effectively what we're saying is that whatever we have, we should put a lot of emphasis and a lot of energy at making use of it for longer. Because once we've built it, it's built and it's done, and there is little we can do about it. Recycling is a big issue. It should be improved, but recycling is not the panacea. It should be the last resort. of when nothing else is possible, then we consider recycling. But first, can we use less of what we have? Can we rethink whether we can use it or we really need to use it at all? I mean, this morning we had a lot of talks about innovative uses of technology, and some of them are definitely worth investigating from a research perspective. But does it really bring value that justify the cost is sort of question we need to be asking ourselves. And it's not fun to be the person in the room telling those things like, yeah, it's kind of fun generating video by just typing text, but we should keep in mind the consequences, the real world consequences this has. And we don't have so many, strong publication record about this because we like primary data of the cost of manufacturing things. There's no current consistency of how those numbers should be combined together to arrive to a good estimate. It's complicated, but I'm happy to talk about this more out of band.
Okay, let's have 2 more questions. So one's there.
Yeah, my question goes is why, in your opinion, the recycling industry has not been developed that much if it's such a burden? The manufacturing is, as you said, is a catastrophe environmentally. Why do you think it is due to economic reasons? Is due to something else? What do you think? Because, for instance, if you need to recycle ICT elements, screens, computers, chips and PCBs, and these things have been existing since the 80s. So it's already 40 years we have these items. Why the recycling technology hasn't kept up with the pace, according to, well, anyone?
I mean, I can. So it's my high-level feeling about this is that it's actually very simple. There is a driving objective. The primary driving objective is to make things cheap. And that is sufficient to explain a lot of things that is going on. And making things recyclable is not cheap. It's not the cheapest way of doing things. But the cheapest way of doing things is to have highly integrated components that you can fit in a smartphone that are custom made for that particular purpose. And they're not composable. And so you cannot really easily take them apart. You don't have processes that are made from the beginning to be recyclable. And you can do that, and I'm pretty sure engineers would know how to progress on that front, but it has a cost. And so, I don't know how much are sold the newest iPhones, way too much, right? But the cost is still very, very small compared to what is packed in. And the cost is kept so low at a price. And the price comes that it's very hard to repair. It's very hard to recycle. You can make this better. And in Switzerland, there's the Fairphone brand is very popular for that purpose. But the phone costs like 3 times as much as like another brand for performance that are honestly not as good. Right? So are the consumer willing to pay for that additional cost for recycling, which is something they don't see, that they are not the one doing? No. The reality is that today this is not happening.
Yeah, maybe to add, so I think he had the main point already, doing cheap and all the, for example, the rare earth metals and critical materials are in so small components in combined materials, and that it's difficult to recycle. And as you know, the vendors rather sell you a new phone than make you repair it, because it's better to sell new stuff. One very good example following the Fairphone is HMD, which used to be branded Nokia, but these HMD phones are built so that you can replace the battery and screen at home. So I think all their models nowadays, I think, are repairable. So they have, I guess, taken seriously this direction. I think they are relatively okay in terms of performance and so forth, and cheap, like less than 200 euros, I think, is the cheapest versions. So they have taken the step that, hey, now these are repairable. Laptops, I've never heard that there is a single laptop or that could be repaired. So if there is no incentive for companies to do that, then they're not going to do that, or there is a mandating something. I think the USB-C charging thingy from EU, which put Apple to change the charging charging interfaces was brilliant example of how you can do things, when if your companies don't, do it, then, eventually they have to do it. So the repairability is something that, EU could take much stronger, impact and opinion on that. And the devices need to be repairable, built for repairability, but also for, as I mentioned, economic repairability. That if it costs more to repair than buying a new one, then no citizen will do that. So it has to be also affordable to repair. And that's not just ICT, it's, your washing machines, your TVs, I mean, with cars, you have electric cars, you have nowadays the situation that in certain cars, you can't repair the battery, and changing the battery costs more than a new car. I mean, I think Mercedes has done that, and some other brands, I think Porsche has done that. So it's like 50,000 euros plus work to change your battery because you can't repair it. So the car industry is also doing that, at least some vendors. So
let's have okay, go ahead, you have a question? Okay, there's Maria and you, and then we will finish.
So you talked about the sustainability of manufacturing that impacts AI, right? But I wanted to ask you also about your opinion. So training the AI models, already back in 2019, it was said that training an NLP, which is the old LLMs, was the equivalent of 5 cars their whole lifetime in terms of carbon emissions. So obviously this has kept on increasing. This is from a study from Struble, you might be aware of. This has kept on increasing, and what we see now is that it's not only the training that is very carbon emission intensive, but also the inference, so using it, right? Yeah. Now, in terms of user, AI is kind of free for everyone. At most, you pay for a license for this or that, but we don't really pay for the energy consumption or for indirectly the carbon emissions. I've heard some talks about the possibility that maybe the big AI companies should be charged more, so not a linear rate, but kind of an exponential rate, so that they start being careful about that, or that users will be charged per let's say, query or token. Could you maybe give your opinion and expand a little bit on that, if possible?
Is this going on record? Hopefully not. It is. Okay, then I need to take 15 minutes to think about an answer. But I mean, that's really the problem I see with ICT, is that it's kind of hidden. For us, it's the laptop, the small phone, and you don't see the huge infrastructure behind that. But I mean, let's say, as an example, what this take the food, for example, this bio or natural produced foods and whatever it's called in English, this, environmentally versions of, apples and milk and whatever. It's not the #1 product anyway. It's often a bit more pricey, so people take the normal version. So unfortunately, price has an impact on here in ICT. So I don't see any other way, because I mean, people take the green solution if it's convenient, but if it's not, then they don't. So you can also put that on the end user side. So I don't know if there's any other way than, some economic incentive that, you use a service and you use a product and you pay for it, and then you are, careful about using it. Or if you just use ChatGPT for the fun of it, and, it doesn't cost anything, then of course, all that inferring is putting stress. But as Romain said, on one hand, we need to understand that when the infrastructure is there, like the data centers, and they are powered on, if no one uses them, they are still powered on. I mean, so in that sense, as soon as you power them on, you might as well use them. I think the example of fiber networks is even worse, because in fiber network, when you put the switch on, it's like 95% power consumption already, even without the signal bit transmitted, because the laser is on, so the power consumption is up already. So it doesn't really matter if you use it or not, it's still up. So of course, if the ICT infrastructure would scale So there is power proportionality. Then, you know, if you don't use it, there's no consumption. If you use it, there's consumption. So that at least would help a bit. That's what happened in wireless, but that's not Romain's any area, and he skipped that part. But in wireless networks, you do that. So if there's no, you know, usage, you kill the base station, you put it out at night time. So it helps a bit, but I don't know what else motivates the money. Sorry, I'm being, you know, how would I say, realistic or pessimistic.
And yeah, last question, Sonia.
Okay, thank you. Thank you very much for all of you for this great talk. For me, it's maybe more a thought because for we as users of digital technologies, whenever we have a huge amount of storage capabilities, we have digital infrastructure devices, so the companies are providing more and more digital services, and because they need to do to provide new services and make money and to do business. And for us as users, we have these all of these services, so we will continue to use them. So maybe the question is to educate the users and the kids in the very early age about the impact of the use of these services. So education. And when I was hearing to your talks, I was wondering if our work to do the AI models and the algorithms more frugal and using a more smaller AI agent communicating and working in more responsible way. I don't know if it's if it's still having sense to do that, because if the most huge impact is on manufacturing. So I'm wondering what you are thinking about, if it makes sense to continue doing research on the more frugal AI.
Maybe I'll let the AI people answer, but for the first part, then I have this, you know, 5-credit course at Aalto, which by the way will be, you know, open in future in Europe. But on my last lecture, I take the topic of digital sufficiency. So what is enough? To make the students think about what is enough ICT. Seems to be that there is not the concept of enough. Of course, there's limited hours in the day that, you know, there's a limit on that, but just thinking about that, you know, what is enough of ICT? Philosophical discussion. I don't have an answer, a mathematical number, but if there's any AI people want to comment on the
So maybe on the inference, I think we still need to optimize the model for sure, right? So quantization, pruning, distillation, and this kind of things. The agentic frameworks are coming, right? So because you can also have much more accuracy when you have small models talking each other, right, compared to a big one. It doesn't solve the problem of the life cycle, right? But the energy consumption is also a real problem, right? So the guys, Microsoft in the US, they are reopening a nuclear plant, right? So the 3 Mile Island, 800 megawatts, just to put a data center, right? It's a real issue. Life cycle is an issue for sure. Power consumption is another one, right? So we are building data center now at 1 gigawatt capacity, right? So you need a nuclear plant. There is no other way to do that, right? You need to sit your nuclear plant, close the data center. And it seems to be quite cheap to buy a nuclear plant, right? So because there are so many money, right, in that industry today that now buying a nuclear plant doesn't seem to be the issue, right? So yeah, I'm not sure it's a good news, but so regulation here, right? We are not in the US, in Europe, but I don't know if a private company can do that. I hope no. But in the US, it's the case, right? So,
no, just think about if the ICT industry starts to need its own nuclear power plants. We are way out in the wrong direction if, you know, you start to need your own private nuclear power plant.
Just if I make quickly a clear answer, or that's an opinion, right? On your question about is frugal AI something relevant? My personal opinion is yes, very strong and unambiguous yes. Why? Precisely because of those direct versus systemic effect I was trying to explain in my talk. Like the direct cost of the energy usage may be small, like nuclear size small, right? So it's still not that small, but that's the direct cost, right? And one should not forget that by reducing the amount of energy used per task, that means we can fit more tasks in the same power envelope, right? And so if we don't do that and say, well, the energy usage is not that big of an issue anyway, the embodied is, then we will eventually build more data center to produce the same workload. There are two independent issues, which is we should rethink when and where and for what purpose we use any sort of technology, right? It's easy to bash on AI because that's the big thing right now. I think we should be more diligent in the use case, but it is very useful for many practical usage. And so research in that direction is totally valid and required, in my opinion. But making it as energy efficient as possible will always help. And that's something we need to keep in mind. Of course, we also need to be wary about the rebound effects that as we make it more efficient, we may use it more and more. And that's the catastrophe with LLMs right now. Just like it's so sexy and so appealing that it's everywhere because we can afford it, because the operational cost of it is negligible. The question just before was about, you asked about the cost of inference versus training. People that work in AI development know for a very long time that already now inference would be the dominating factors in terms of costs. We've reached that point. We've crossed that boundary a couple of years ago. But okay, I've lost my train of thoughts. Yes, what I wanted to say, you mentioned the license for OpenAI, for example. OpenAI operates as a loss. Like when for every single license, you pay $20 a month to access ChatGPT, whatever the average user costs more than this amount of money to OpenAI. This still exactly, like they see this as a long-term investment for something like that's not. This is small money for them in aggregate. Like yes, they make a loss on the licensing. It's because we are reasoning in terms of money, but until we have a very strong carbon tax, we're not going to fix it with money because the economic incentive will bias things in the wrong way. And a quick point to your other question about education. There's actually going out next week a comics that has been put together by researchers at EPFL, which is called Utopia. So yeah, play of word that works only in French. That is precisely to try to target this point and try to put into perspective the fact that artificial intelligence is something that has very real physical manifestation. It needs to run somewhere. It has an impact. And try to depict from the news that I could read from the EPFL, both like the positive potential and the real physical world impact that could serve, and it's targeted at teenagers.
Also, it's our students and the future developers to take into account impact wide design. Sorry? Yes, I was typically very short.
Just I have a mic or
Yeah, I think the question that Sonia posed is very important because today there is let's take a specific application, demand forecasting tools. They have been developed for decades. Okay, there is a community that they have their way to evaluate the tools, and each time there is the traditional statistical models, etc. They say, okay, this is the best tool. Now the change in this area is that new players come into the game and propose new tools that they don't belong to this community. I was in a conference 1 month ago where I saw a company that provides a large generative solution saying, okay, now we are here, we are solving the problem of demand forecasting. Okay, and our model is the best from anything that exists. And they had compared with what? Their reference was a naive model that says, okay, to predict the demand of tomorrow, we use the demand of yesterday or the same week, last week, okay? So the problem is, and I review papers and I see this systematically, that all these people that try to promote solutions, especially industrials, based on generative AI, etc., they put so low the reference that they present huge improvements, and they don't use state-of-the-art models or reference models. And in forecasting, for example, we have the principle of parsimonies between two models of the same accuracy. Use the simplest one, and we have made comparisons, and we have very simple models that do the same, have the same performance in demand forecasting as generative models. So I think what we have not succeeded so far, the different communities, especially this one, but I think this repeats to others, is to establish protocols, evaluation protocols, and methods to certify somehow the tools, so that when you propose something, you know where the performance places compared to the state of the art in an objective way. That way, if you propose some frugal method, which is better to this and this and this criterion, you can convince people. But now there is not, these evaluation methods are not standardized in areas by area. So you cannot, finally, you cannot convince people. It's, you know, the one who wins is the one who has the best marketing and says that he can solve all the problems. So it's a bit, what appears now, it's a bit of a transition to a kind of jungle where we have, you know, before the community was knowing what each other is developing, but now people who do not neglect completely all the history, etc., the reference models, come and they say, we are the best. Why? Because they put the reference very low.
Yeah, maybe we can use what is done, for example, in telecommunication for standardization systems, or in cybersecurity, also for AI, to have some standards which all the developers need to respect, and to provide some guarantees on frugality, on security, and on reliability also.
Okay, I think there's one question. Okay, so let's do the very last question. Let's keep it short and we finish.
Well, this is more, yeah, it's a question, but I guess we will not have an answer. We have been talking about nuclear energy, and what do we do if by political reasons our government in our different various countries just cancel that type of energy, like is the case right now in Spain. So they're going to shut down all the nuclear base in, I think it's 5 or 6 years. It doesn't make sense to me, but this is what is happening. So how do you convince people that are without data or without knowledge of what they are talking about to do that? The feeling of the society is that, oh, this is terrible for us. Do you have an answer to that?
I have an opinion, but
Well, the only answer I have is what happened a couple of weeks ago in Spain. Yeah, I mean, I guess the jury is still out what was the reason, but at least I read some of those that, you know, one of the challenges is that the frequency fluctuation caused by renewable energy. So, I mean, that's what's going to happen in Finland also if we are not careful, and that's going to happen everywhere else if we're not careful, because I mean, the renewable is great when you have sun and wind, and if you don't, then what do you do then? Or you shut down the country when it's not windy.
no, yeah. So I think
So maybe in Europe, one idea would be on, I think one limitation we have in Europe is we are not building a very large data center, right? Because the advantage of OpenAI and these kind of guys are Grok, right? So they have access to so many GPUs that maybe at the frontier level of the model, right? They can see things that we are not able to see in our small clusters, right? A big clusters in Europe is 16,000 GPUs, right? A big cluster in the US is 500,000 of GPUs. So I think they have access to practicability of things they can see from the models, very large models, that today we don't see in Europe. So I think, and we don't have to build that everywhere in Europe, right? So, but at least to build this kind of installation and then to be very efficient on the rest, right? Because, and then on the model, I think from the industry point of view, my understanding is that, okay, we know the OpenAI and those guys, but all the other guys, they are moving to the small models, right? Because they want to put the models on that or in your car or everywhere, right? So I don't know if it is good or not, but the go-to-market or the business model of OpenAI is known as not successful, right? Today, they are successful because they have a lot of money, so the valuation of the company is very high. But what they are selling is the return of investment is not there, right? So it will be maybe never there, right? Because it's a consumer market. All the other guys, they are going for small model, right? So for a B2B kind of approach, but it's small model for inference. That could be a distillation from very big model. And today, the limitation I see in Europe, we don't have the kind of data center allowing us to train very large model.
I have the answer. Let's go back to the 80s. And the point is that in the 80s, computers were not very powerful. So programmers actually had to think what is the software they are writing. Even in the 80s, early 2000, you had more ideas that you had computing power. So actually you had to think what you write in terms of software or models on inference. We have forgotten that. Everybody's had forgotten that. And that's, now people are talking about green coding. Green coding is 80s coding, when you actually do what's right to do instead of expecting you have, a million GPUs and then you can do whatever crap in your software and then you just have power. Let's go back to writing 80s software.
Okay, with this thought, let's finish here in this session. So thank you everyone for coming. For the people on Zoom, we are going to have lunch now, so we'll be back sharp at 2 p.m. Nothing else, so thank you very much to all our panelists.